Hi, my name is Bob Mcguire. I'm N4HY. I live near Auburn University in Alabama. I'm recently retired as the chief scientist for the Hume Center at Virginia Tech, which is currently the largest funded research center at Virginia Tech, where I did software-defined radio and lots of other things, including machine learning applied to problems for which we received contracts and grants and educated lots of students. So I learned about machine learning in applying it to a radio problem, which I will discuss later. But it led me to think that this kind of activity might be useful for ham radio. So I'm going to pursue it. I'm going to tell you how I'm going to do it. Let's start right at the beginning. What is machine learning? I'm sure lots of you have heard of deep learning and machine learning and all sorts of things. What is any of this? And what will it mean to us? So let's just start from the beginning. So this is a quote from the CEO of NVIDIA. Machine learning at its most basic is the practice of using algorithms or computer programs to data, learn from it, and then making a determination or prediction about something in the world, something in the environment predicted by what the data is telling us. That's a little tough to kind of get through, but this one from Andrew Ng is a famous machine learning person at Stanford University. Machine learning is the science of getting computers to act without being explicitly programmed. That's pretty good. That's a little better, a little more easy to understand. Machine learning is based on algorithms that can learn from data without relying on rules-based programming. So now we're getting down to it. We don't want the computer to have to write down rules to make decisions or classifications or determinations with a human involved at all. So that's the goal. But are we there? Let's see. So machine learning algorithms can figure out how to perform important tasks by generalizing from examples. That's also a form of machine learning. And how to generalize a trained algorithm is a part of the issues that all of us need to face when dealing with a computer trying to apply learning. Machine learning is the ability of the machine to learn on its own. Now that's the most general of these, and it's of course a very lofty goal. And so major steps have been made. I mean, you see this every single day. You're on, say, your cell phone or on your computer, and you ask Google or another search engine, or talk to your phone, or ask for directions from your GPS module, and all those things. Machine learning is there to interpret what you ask, and after it's classified and determined what you've asked, it then executes an action, and that is also machine learning. Let's just keep going and see where we can get with these kind of really high-level descriptions of machine learning. Well, for now, machine learning is exactly like this. You got a couple of machines, and a person is trying to orchestrate what they're doing. Now, it's less like sitting down and writing a program, but a human is still involved. And for right now, that is just the nature of the beast. And so we're teaching these computers how to learn from data, mostly using heuristics. Now, these heuristics have an extremely firm foundation, but as with all these extremely firm foundations, there's caveats that one needs to understand so you don't make a mistake or misapply what you get. So there's the universal approximation theorem, which was a really major finding that a lot of people didn't believe. So let's have a bunch of data as inputs to a black box. And the universal approximation theorem says that if you've got a bunch of neural nets doing something inside this black box, that you can do with a finite number of neural nets, get as close to the actual realistic output given that data as you want by increasing the complexity of the neural nets inside. So you can get there. You can actually train neural nets, take in input data to get as close as you want to the actual real function you want on operating on that data. Now that is a big deal. It doesn't tell you how to do it. It just says you can do it. So this is one of the major kinds of problems or issues with these kinds of theorems. It's an existence theorem without how to do the construction. It's not a construction process, it's an existence theorem. So one of the major techniques that is used for trying to get a universal approximation based situation, machine, algorithm, etc., to learn something from the data is done by stochastic gradient descent. And we're going to go through how that's done without going at a high level, without actually getting down to the nitty-gritty details. But just let me tell you, until the 2000s, really 2008 or thereabouts, the stochastic gradient descent was known, but it just was completely impractical. And then Hinton, Geoffrey Hinton, a well-known computer scientist, took a set of handwritten letters and alphabet, and mostly numbers in the beginning, and trained a computer to recognize these handwritten numerals on automatic pilot without a person telling them what to do. So he figured out how to train it. And it was a stochastic gradient descent algorithm, and he called it back propagation. So there is a way to tell the computer, given input data, and it make a guess, how well did it do? So it's in critical importance that from the beginning, when you're applying machine learning, you have a way to tell the computer how well did it do. So again, those two things, stochastic gradient descent and universal approximation theorem, there's a hidden secret. We pretend they apply perfectly, and therefore we're talking about heuristics. There are some theorems, but again, in general, we don't actually know for certain when we start this process of machine learning training, it will actually work. So what do machine learning techniques do? So of all these weird things on the left, how do we get to a place where they are ready, trained, and ready to work? Well, first, we have to have data. We have to have input data of the type we want to present at random whenever we want to. We have to have data from that class so that we can train the machine how to recognize it's from that class and do something useful with it. So lots and lots of data. And right now, data is an extremely important and expensive part. From that data, we want to derive a model. And a model is a machine learning algorithm that we're going to construct by doing iterative analysis on the data. So how does the iterative analysis work? So we take data, we feed it into our model, we get an output, and then we have an objective function. The objective function measures how close your predicted output is to the actual one you desire. And we will go over some examples to make this clear. And this process of data, model, objective function, and feedback is the optimization algorithm. And the optimization algorithm, as we feed this the error back through, is an instance of a stochastic gradient descent algorithm. So what are the machine learning types? We'll go over these, and I don't expect you to remember them, but I'm just going over them for completeness. And they are illustrative of kind of things we have to think about. Unsupervised learning is where you don't know anything about the data. You don't know how to label it. And so you take these pieces of data and you feed them into algorithms, and the algorithms that you feed them to discover structure, discover meaningful ways to compress that data into classes. And from this, you find features in the data as presented to this machine learning algorithm, which allows you to put the data into different boxes. And so this unsupervised learning was how everything was done until we got very, very good at doing a different kind of learning. Supervised learning is where you still have lots and lots of data, but you feed the data to your machine and you know what the output should be while you're training. And you're going through, looking at the output of the machine and saying, look, you're in error. And here's the error. And here's how bad the error is. And based on that input, it corrects itself. It learns how to do better slowly over time with lots and lots of data. Semi-supervised, that's where like website classification and speech analysis, face recognition, customer segmentation, where the like kind of things you see on Google or your phone when it's recognizing your voice, or you enter a search term and it's doing the best it can. So this is semi-supervised in that some supervised learning goes in and then it generalizes from there. And the generalization is not done with much supervision. That's an example. Reinforcement learning is really, really neat. You take your problem and you have some input data, which in this case, the data is describing the current environment and the state of your system. And you let the machine learning based model take the data and the current status and compute an action. And then the action is taken by the system and you get feedback on whether or not the action was good and appropriate, whether you got the reward, you've got your dog got its food from clicking on the lever, or it didn't. And then it goes on and learns from that without human intervention. And we've seen some spectacular examples, which I will go over later. And then anomaly detection, such as credit card fraud or a cyber intrusion, is a major growing area in machine learning, and it's badly needed because we've all seen all the headlines about all the fraud and cyber intrusions lately. We really need machines to be able to help us do this, since we don't have enough manpower to do it, even if we knew how. So unsupervised learning is demonstrated by these pictures on the right. So a kid playing with toys and doing things with it, that's unsupervised learning. And the robot is taking a bunch of stuff and trying to figure out how to classify them or name them or cluster them into the different groups. This is typical of unsupervised learning, and it is really how kids learn a lot. It's for the most part. So it isn't completely random. Of course it's not. The robot can't classify things in a vacuum, and the kid can't learn from things that aren't there. So in both these cases, data and or things, objects, words, pictures, whatever, are placed in front of the child or the robot or the computer, and you are influencing the things it has available to it to learn from. So you bias and or guide the learning by what you expose the learning system to. Then the child, computer, robot learns to separate things into classes or groups. So for example, down on the floor in front of the child are dinosaurs and a tiger. And maybe after a little bit of playing, the kid can tell the difference between a dinosaur, an alligator, and the tiger. They're different. So unsupervised learning can be a goal in itself, discovering hidden patterns in data that you didn't know that were there in the beginning, or you would have done it already, or it's a means towards an end in learning a feature. So if you have a feature that you did not know was in the data and your machine helped you learn the feature, then you can use that feature in how to use the data. And the reinforcement learning algorithm, it's where you have an agent, which is your computer, and it has a policy that says, if I see the environment and I know what state my system is in, based on this policy, I will tell the system to take an action. So given a state and a policy and a reading on the environment, the agent says, take this action. And if the action is good, do you evaluate the policy by giving yourself a reward? And so if you start losing out on rewards, that means you need to update your policy. But since you've evaluated your policy as not being correct, you want to modify the policy. So that's one version of this. And so this goes around in a loop until eventually you begin getting more and more and more reward for the action, for the modifications you've made to your machine learning model. And we have spectacular examples. One of the first spectacular ones where basically nothing was told to the machine, and it had these screens while it was playing Atari and the Atari machines, and it learned how to win these games better than any human that ever played them by trial and error and getting a feedback on how well it did and a reward for doing better. And then the one I thought basically would not happen before I died, but did anyway, there's so much for my intuition, was the Go game, which is by many people's opinion and some difficulty classification based on some pretty difficult mathematics. Go is really difficult. But the computer, given the Go stones, playing against humans and then later against itself, can learn how to win Go better than any human that ever played the game. And that was really surprising. And it didn't take that long. It was a few days from scratch after they learned the right algorithm for updating the game. And so these are spectacular things. Okay, so what do we want to do? Well, last but not least, since it's kind of where we're going here, is supervised learning. So let's start in the center where you've got the teacher telling the two robots, giving them a lesson. That's kind of how you want to think about it. So again, an example in the upper left is the teacher showing the robot pictures, and when it gets it right, it's told yes, and when it gets it wrong, it's told no. And it does this over and over and over again. And there's this algorithm that updates the robot's knowledge based on what it sees, and it gets better and better over time at getting the right answer. So let's look in the upper right. So once the model has converged and is doing the right thing, by you first giving it input and telling it these are apples, then are bananas or whatever. So it eventually gets a very high probability of getting the right prediction about what it's being shown. So that's the goal, is over time being shown lots of examples where it guesses the answer, and then you tell it what the real answer is, and it grades itself based on a objective function, how well it did, and it learns how to do better from repeating this over and over. This is repetition learning at its best. So kind of a more algorithmic presentation is you've got training data you feed into your algorithm, and the machine learning model issues a guess, and then it's graded on the guess. This picture is of a trained model. So now you've got a model where it's been trained, and you've given it unseen and unlabeled data, and it picks the right answer. That's a good thing. Your machine model is trained. And this is us as hams for now. I think this is really what we can do. And this is what we should do on some really interesting problems. So let's go from there. So look, this is www.sigidwiki.com. And it has some really interesting things on it, which I think are very useful. It has frequency bands, and in these frequency bands, it has identified signals and unidentified signals. And to the extent possible, they have been further classified into these classes, military, radar, et cetera, down through time. So all of us know time signals that are on the air, and we've all heard number stations, and we've also heard interference, and we've also seen noise, which is rare and inactive. So this is the kinds of things that would allow us to have data which we can use to train our models. So my initial goal is to take things that are in HF and VHF, and using the kind of categories that are in here and some instances of the data that's actually in the database for this website, and do some initial training, and then figure out where to go from there with the machine learning models. But I want to use this data in here in the beginning, because there's 424 classified and identified signals, and quite a few, about half of them are unidentified, which is interesting. The thing I fear is the unidentified signals will have very few pieces of data in which to learn from, but that's part of the project anyway. So friends can help. So I have these two friends that have data. Jeffrey Moss, K8ND, is a big time contester, and both in contests and not in contests, Jeffrey has recorded many hours of HF data. And he has 8 terabytes of data just from HF contests. And that's a good case where you've got lots and lots and lots of instances of signals, and they need to be marked and told what the signal is, so that that data can, with the signal recorded and the data marked, that can be used as training data for learning one of these machine learning models in a supervised learning program. And now you're getting an idea of where I want to go. So Phil Karn, KA9Q, well-known radio amateur, member of AMSAT Tapper, president of ARDC, has gotten enamored of taking software-defined radio and running it on low-end equipment, and he's done the following. He has 4 terabytes and growing of data, listening to the VHF and UHF FM bands, running on a Raspberry Pi, talking to a homebrew software-defined radio with the radio interface, an AirSpy with listening to the VHF and UHF bands. So he has a filter bank, not polyphase. That's wrong. It's a filter bank, but it's not polyphase. And he divides these bands into channels and listens to the signals with an algorithm that tells him whether or not the channel is in use. And so he records the channel if it's in use, and he constantly runs 24 hours a day monitoring the FM bands. So now Phil has given me a device that has actual signals of interest. They are marked as to what they are, and only the snippets that contain usable signal are recorded. And this is a good thing. So in addition to this, we need lots of stuff from the bands that are marked as noise or interference or other things, so we can distinguish the FM signals of choice from the actual noise that's in the band. Okay, so look, one of the things you got to have if you want to train one of these machine learning models is a supercomputer. And so I've built one. And so this is with the side off and all the things dangling out to be able to easily take a picture of them. So in the upper right with all the colorful things, upper left where all the colorful things are, you see in the center this circular thing with TT on it. That's for thermal take. That is a water cooled jacket sitting on top of an AMD Threadripper processor, the 3970X, which has 32 cores and 64 threads. So that's quite a computer. Lots of cache so that things are easily moved in and out quickly, so long as you're running tight algorithms and over data that's arranged in blocks, it can do it easily and really get some speed up. So you see these vertical bars to the left and to the right of bars of light to the left and to the right of the the water jacket for the processor. That's DDR memory, and that's 256 gigabytes of very fast memory. And above the memory and the processor with its water jacket, you see these colorful fans. And behind the colorful fans is a water reservoir. And below the thermal talkie jacket, you see these pipes. They go up to the reservoir. So warmed water goes into the reservoir, which has ribbed fins on it. The fan cools the water that's inside the reservoir and feeds back cooler water to the processor and controls the temperature of the processor. So just let me tell you up front, that is not cheap. It's just not. And so I hope, let me say from the outset, this is not something you need. And that's a good thing, because you need one or two people that have these kinds of things and are able and capable of using them to train the models. So in the below that picture, there are these two horizontal bars with a bow tie on the left, and you see the word GeoForce on them. It's covered up as GeoForce RTX. These are high-end GPUs, and these are GeoForce RTX 3090s, and there are two of them. So between the processor, memory, cooler, and those two GPUs, and another little piece I'll tell you about, that's a fairly serious used car or something like that. It's not cheap. So, but it's needed, and I'll tell you why. Later. So the thing I want to point out to you is this bow tie right here on the left side of these cards. So what that bow tie does is gang these two graphics processing cards together, so that under certain circumstances and under the right control, they can work together. And why do these graphics cards matter? The mathematics that is needed to do the stochastic gradient descent algorithm to train these models is best done on GPU cards that have certain technical capabilities inside them. And I'm just going to tell you what it is without going into any explanation. They have these tensor processing units in them, which is really, really helpful to doing machine learning. And to point out to you the supercomputer nature here is up here, you can see that I've got a version of top telling me that I'm right now, while it's sitting in idle, using 2.5 gigabytes of the 252 that is available for the user. And you can see that there's 2 gigs of swap, and basically I've got nothing running now. So you only see the little wiggles for things the machine is doing. You can really tax this thing to the max, where all the threads are running, and the machine is really getting taxed to its limits. And these fans spin up really loud, and the water flows really fast, and it keeps the processor cool enough so that it can keep running even at full tilt. So these graphics processing cards down here, and this water cooling and this processor, they consume a lot of power. And down here you see the EVGA 1600 watt computer power supply. That's where almost all of these cables are going, are feeding power to these things. So it's 1600 watts, and I've run these GPUs flat out with the processor running flat out, and it has a 1350 watt steady state. And it spikes a little bit above that, but 1350 watts is kind of the steady state limit for the things I'll be doing. And over here is just another view of the CPUs and what they're doing. So this is a true supercomputer. And for 10 years ago, I couldn't have dreamed of owning this. I would have had to go to work to get access to anything like it. And frankly, I didn't have a computer that would do what this one would do. So you're getting into this age where computer complexity and computer capabilities are just really taking off and going through the roof. So it's just a really great thing, and that we now have access to these things. And it's affordable for a person who is really serious and wants to do it at home. And I'm very feel very, very lucky to have the resources to be able to put this computer together at home and do the work that's needed. So this is the computer, but you also need some software. So I'm just giving you an example of one here, which is very, very popular and is likely to be used in this work. And this is TensorFlow. And I've just shown you on the left side here, the opening web page when you go to TensorFlow. And it tells you how to install it, how to set other things up, gives you examples of how to do computer training. And so I want to go over one here in this picture that is illustrative of the kind of things we are doing. So there's a basic classification. Notice that's a basic one. That's a training program. And literally what we're about to try to do and apply is technically equivalent to this basic learning algorithm. So I'm very high confidence that it will work. And there are other reasons I'm very confident. So we're going to take, we're going to take a bunch of data, and like it's done here. And you'll notice this down here, what these little tiles in this picture are that you can barely see are instances of clothing. So these are pictures of different types of clothing. And this computer has had lots and lots of data in the form of these pictures of clothing where the data has been marked with the name and type of the clothing. Maybe also marked for color or whether or not it's typically worn by a female or typically worn by a male or unisex or whatever. Just all these kinds of things can be included in a training algorithm for the computer to later be presented with a picture of one that it does not know the answer to and get the answer right just by looking at the picture. So you give the computer lots and lots and lots and lots of examples. Tell it when it gets it right, tell it when it gets it wrong and how bad it got it wrong, and then let it iterate. This happens over and over and over and over again to the point where you burn lots of power on your computer, and finally the model converges to a set of parameters that when a model is applied to a picture that's of unknown clothing, it gets close to the right answer almost all the time. This is when you're doing good. Okay, so look, we've got some other target hardware, which I think is of interest. So the AirSpy is on the right and the HackRF1 is on the left. So the AirSpy also comes with a converter that allows you to listen to HF, and the HackRF that listens to HF, VHF, UHF, and up. So both of these will be software-defined radios that I will be using in order to do testing of the trained algorithms. Where will I run the trained algorithm? In the center is a Jetson Nano 2 GB processor version. This is a development board, but it's really what we need. Okay, so it has 2 GB of RAM. So you're not going to be playing major games on it or running a lot of graphics. You're going to have it doing number crunching. And it has a fairly high-powered GPU on it. And you take your model, you tell the program you're going to run on it to, when data comes in, run the model on the data, tell me the answer. So that's what this thing will do. And it has a fairly high-end ARM processor with 4 cores, 2 GB of RAM, and the cost, and a GPU, and the cost is $59. So I'm going to start with the least expensive one of these. It has a fairly high clock rate on both the GPU and the ARM, and we'll see how well it does. And if this is not enough, the next one up is 4 GB with 6 cores, and it is $100. And then right above that is another one, which has many gigabytes of memory. So they vary. There are several stages of them. One of them 59, one's 100, one's 300, and one is 700. I don't believe we will need the $700 one. We might need the $400 one, but I don't believe so. I believe the $59 one or the $100 one will allow us to take signals off the air, capture them in a way that the computer can understand, tell it to classify the thing we've given it, and it will issue an answer. I believe that we can do that. And the reason I believe we can do that is because a student and I have done it before. So a student who's a ham radio operator earned his master's in electrical communications, electrical engineering under me while at Virginia Tech. And we did classifying, identifying types, etc., building an SDR from it for a frequency hopping radio for MITRE and the US Army. Now, I'm not going to tell you the target because I'm not allowed to, but this kind of work informed me of what we can do. And so it did supervised learning, TensorFlow and Keras was used. The entire program, learning and application were done in Python calling libraries. This is the work that will be adapted for this problem. And so we will not be taking the frequency hopping radios of interest to MITRE and the Army. We will be taking signals that we get off the air from our own means and train the algorithms to do it that way. But essentially, many of you will have seen a waterfall algorithm. So a waterfall algorithm streams down the page and shows you the spectrum of signals. So if a signal comes on the air, you can detect in the waterfall when something is there. And then you'll grab a block of it and feed it to the computer algorithm that's done the machine learning algorithm, and it will classify the signal to the best of its ability and then pass it off to the next part, which will have a higher grade process running on a software-defined radio to doing even better work. So that's kind of the cascaded flow of things that are intended. And the reason I know it works is because we did it on a really hard problem for MITRE and the Army. So we'll gather data from K8ND and K89Q and others and store locally on a large array that'll be inside this machine. And so all the stuff will be contained in one box. That allows us to do lots and lots of training on lots and lots of signals at very high speed. And once we have the classification of the signal in terms of type and other parameters that are needed, we can automatically build, say, a GNU radio algorithm to process the signals ID'd by deep learning and the neural trained deep learning algorithms done by this project. Now, what are the promises? The promises are this will all be open source, open specification. GPL algorithms will be done in GNU radio, and the Python training algorithms will be published, and how the models are derived will be published, and it'll all run on commercial off-the-shelf hardware that anyone can purchase. So I think this is, we've finally gotten to this place where the application hardware and the training hardware is purchasable by individuals, and the individual person who just wants to test the algorithms to see how well it does in classifying signals on the air, hopefully giving us feedback so that we can learn to do better, will make this available to lots and lots of people, because these software-defined radios and these special purpose ARM-based GPU-enabled learning computers are getting very inexpensive. It's like this technological revolution is enabling us to do some really neat stuff. So look, just want you to know, you never underestimate the power of a grandpa with a math degree. And I've done some interesting things with my signal processing. That's me on top of the USS Hampton right before we went under, and I stayed under for months. So software-defined radio with machine learning enabled tools that allow you to figure out what some signals are and how to process them are really things that are of very great interest. And I'm in Echo Mike 72 IP. My DMR is 315-1472. I'm available through a hotspot, and that's my email in case you want to contact me. I'm looking for other people who are interested. And with that, we'll stop here and take some questions if we have time and that's allowed.
Okay, Bob, I'm going to ask you some questions from the audience.
I just want to show people the beast over my shoulder. This room is really hot with that door closed.
Very good. Okay, yes, as you can see over his shoulder is the computer in question. So about the computer, I'm going to lead off with a question earlier in the chat, and then I'll move to the Q&A tab. Actually, several questions in chat. I see them. So why have this computer at your house? Why not do your number crunching in the cloud, like from AWS or from the other servers?
So I believe that this work is going to take quite a bit of time and quite a bit of data. And I've worked on another project, which people can go find out about easily. It's called Skyhub. And I spent $5,000 in the last year just paying for the cloud storage.
Okay, so it's a question of cost. If you buy your computer at home, then you have a cost, you set it up.
3 years of that, and you've paid for that computer.
Okay. All right, so that entered into your calculation from your experiences with using cloud-based number crunching.
Yep. It's available. You can do it, but training this algorithm to discriminate from hundreds of signals is going to take thousands of hours, and thousands of hours on a cloud-based GPU-enabled computer with cloud storage is very expensive.
Okay, and which of course may change in the future, but for now in the foreseeable future, this is okay.
It's going to get cheaper, but it's not now.
The next question is there a current GitHub repository for your work? How will people get involved and where will it be?
Okay, so I do have a GitHub. I'm N4HY on GitHub. There will be a repository. It's not there now, but it will be. And there will be, the readme.md. And I believe what I'm going to use is Rocket Chat to enable people to talk to each other and collaborate. And so it'll be GitHub and Rocket Chat is how I think we'll do it. And so I am expecting this work to receive some support from a granting entity, and we'll just go from there. I'd like for this to be almost zero cost to those who want to do work, so that, like Michelle and ORI, there will be the hardware and software and other things will be available for people to play on and try stuff. So my own HF and VHF gear will sit on the net in a demilitarized zone, so that others can use it to do some of the software-defined radio testing. And it's pretty high-end flex gear.
Okay, thank you. Now we do have a question about what are you actually trying to do? What problem are you trying to solve?
Okay, so I want to automatically look at signals on HF and VHF, not know what they are ahead of time, but I'll being able to apply known data about what occupies the band, see a signal, recognize what it is, and automatically build a software-defined radio program to detect and demodulate it.
Okay, so would you call this an autonomous receiver?
Yes, it's complete with iterative design and robotically enabled.
Okay, very good. There's a question. Are you familiar with the Anon HPSDR spectral noise method, and is this an example of machine learning?
I don't believe its spectral noise algorithm is machine learning. I know of its existence. I don't know how it was derived. So I'm going to plead ignorance on the details.
Okay. All right. I'm going to go to the Q&A tab for a moment, and then I will come back to chat. So what motherboard is in this supercomputer?
It has a Creator TR4X motherboard, and the TR4X is, of course, providing the socket for the AMD Threadripper 3970X.
Okay, and there's a go ahead. I'm so sorry.
Yeah, it's from MSI.
Okay, thank you. And there's a question. Would you call this FLDigi on steroids? It sounds like it's FLDigi plus some intelligence.
Okay. In addition to just classifying what's on our bands. I mean, there's signals popping up on our bands all the time which don't belong there and interfering. We can help identify them and report them.
Yeah, so this sort of work would fall into signals classification.
Signals classification is the first part of what I want to do.
Very good. Okay, Skimmer already does this with SDRs for CW and RTTY signals. How are you different?
Okay, so it will not be limited to CW and RTTY signals. So let's say that right after 9/11, 2001, I applied this to single sideband signals in interesting places.
Another question.
It'll work on all sorts of signals.
Could this also be adapted to work on FPGAs?
The answer is the application of the model to incoming signal can be done on FPGAs. The principal issue that I don't believe is yet decided is the cost, both in time to program and the cost of the device and putting it in a packaging that can be easily deployed. I don't know. I haven't done all those calculations and trade-offs, but I am absolutely open to helping that. And what I'm after is enabling people to do stuff they couldn't do before, using tools they never had before, and doing it at the minimum cost. So whatever it takes, I'm not going to be the boss. I'm going to let the data tell us what to do.
Very good. Question, will this technology be able to detect increasing signal strength and falling signal strength of signals over a pre-specified time period?
It will indeed. So a constant need in these kinds of systems is determine the current noise floor and the current occupancy of any range or collection of frequencies. So that kind of stuff is constant. That runs continuously.
Here's one that I think you might be interested in. It is, have you looked at quantum computing style algorithms for machine learning?
I have. So I began the quantum computing project at Virginia Tech when I was the chief scientist of the Hume Center, and the quantum initiative put forward under the Trump administration. I was one of the people that went to the Office of Science, OSTP, in the White House and helped kind of design it. And then I was helpful in designing the rollout of what that will mean for DoD and the intelligence community. So I've been involved in this in quantum computing since the early ages. I actually did interesting quantum computing work for the government in the early 2000s, before a device actually existed. And I wanted to do this since the earliest days. I was at the 50th anniversary of Los Alamos National Labs when I heard Richard Feynman give a talk on using quantum devices to do quantum simulations. So I've been wanting to do this forever, and I still want to do it. And currently there's a lot of work and a lot of money being spent by our government in the US and governments all over the world, and companies too, trying to figure out how to take quantum and make it advantageous to either their needs or their businesses. So I've been doing quantum computing for a while, and I would love to do it. It's not effective, not practical for us as hams to do it right now.
Okay, thank you. Question, do you use a transformer-based model for signal identification like BERT, GPT-2, etc.?
So I have not used GP2 or GP. I have not done that yet. I'm not averse to doing it. Really, what I'm trying to do is very naive algorithms that take actual digital samples, and the output is a classification. So I think initially, since that's what I'm most comfortable with, that's what I will do, and others I hope will contribute whatever they want to do in addition to this. Since I'm going to be doing my thing and talking to others and listening to their criticism and input, but I also want others to be able to play, and we'll make it an open source project on GitHub where we all can play.
Very good. Do you know if there are any studies to use machine learning to create a better CW decoder or use voice recognition to create a kind of SSB reverse beacon?
So the answer to that is yes. So there are multiple companies that are now applying RF machine learning, and multiple entities and a company applying RF-based machine learning to all sorts of problems. And one of those companies was founded by a student of Dr. Charles Clancy and myself at Virginia Tech. He owns quite a few of the patents in the area, and it's being applied. But that's for private business, and it's all the work is proprietary. What we're trying to do is take the stuff that's open source, was published, and we can use it without any hindrance by patents and other things. So the answer is yes. I know of places where it's being done, and we don't have access to what they are doing.
Do you have any thoughts about using TinyML on Pico or Arduinos to execute built models?
The answer is yes. Hang on just a minute. Do I have it right here? Yeah. Yeah, so I have this. This is the Carl AI TPU from Google. And so there's that, and then you can just plug it into your Arduino or Pi from the USB port and have it execute models. So these are integer-based processors, and so you have to take your very high resolution parameters and reduce the resolution of the parameters fewer bits, so it will apply on the TPUs. But these TPUs boards, they're like well under $100 and getting cheaper. They're very low power, and they are very fast. And I'm just constantly looking for new technology to make things better, faster, cheaper. And I will be trying to place some of these models on that thing to see how far we can go.
Oh, very good. So the next question relates to this. Is there an image available for a Raspberry Pi, perhaps, to recognize different types of modulation? And the person asking the question is mostly interested in like FT8, RTTY, SSTV, those sorts of things.
I am not aware of it.
It sounds like, though, that would be a direction that the work would go in, to try to deploy the models on inexpensive hardware.
Okay, so I am going to wait, and let me tell you what I am waiting on. I know already that Raspberry Pi is coming out with a Raspberry Pi 5 or Raspberry 4 GPU that has GPU hardware on it, and they're going to publish libraries that we can train with our tools. So Raspberry Pi understands this. They are coming. It's going to cost almost no money. Look, this is just going to get easier and easier and cheaper to do. So I'm spending resources now personally and using my expertise to get us started. But I'm just gonna, it's going to like every other project I ever did, it's going to overwhelm me with time, and others will come and take over and run with it. And I am perfectly happy with that. I don't want to do one thing all the rest of my life. I'm kind of an eclectic technical person. I like to learn a thing, make a contribution, get stuff started, and have others come along and do things with me and take over. And that has happened multiple times in my life. It will happen here. And companies and groups like the Raspberry Pi group, they are about to enable us with machine learning technology on a new Raspberry Pi.
And that's one of the major reasons that you've decided to do this as an open source project, is to make it easier for other people to take it and run with it?
Yes, exactly. That and I want to show how to take one of these fancier models and adapt it to the less expensive things that are going to be available, like the Carl TPU, Carl.ai TPU, and the Raspberry Pi GPU or ML processor, so that we can apply it across all sorts of things. And what we have to do is learn the limitations of what those hardwares or what those hardware elements are capable of doing. And then what I found is the Raspberry Pi and Red Pataya and Google and other people doing this, they will take your feedback. So long as it's based on facts and supported by logical arguments, they will listen to you and they will try to make things better.
Do you have, pardon me, hang on, I need to scroll up here. Okay, here's a question. Although quantum computing is not practical right now, what would your thoughts of using quantum-ready encoding schemes be? And then there's a link from Science Direct. So what I'm going to do is I will get that link to you, Bob, later, and we will get that. I will take a note of the person that asked that so that we can get that
I want to make
more direct answer to that, because sure, go ahead.
One comment while we're here is most of the devices that we have available to us now are noisy qubits, and you have to do lots of things to make these noisy qubits usable on your problems. Now, lots of what we're doing is trying to find probabilistic estimates with a range of error for parameters and on the problems that go into machine learning device. So these noisy devices are they can be used, but the problem at the moment is, yes, I can use quantum algorithms on these quantum computers, and they will yield a very fast answer on a very tiny problem. And by the time I take a bigger problem and break it up into small pieces that run on the quantum processor and then glue all that back together in some kind of synthesis, it's cheaper to train with the classical hardware. We are at this place where we can't quite get there with quantum. We want to get there with quantum, and I want my bits to have 2 pi steradians and be a block sphere, but we're not there yet. And so we just So I've signed up to try to get on Xanadu, which is the first real serious attempt to do a photon-based process. But I'm not biased. I'll use ion trap. I'll use frigid cold. I mean, I ran a bunch of algorithms on the D-Wave, which was quantum adiabatic, and was disliked by everyone. But they kept learning and doing better. And so it's just and then Seth Lloyd came along and proved the theorem that quantum adiabatic is equivalent to quantum gate, and gave the transformation and how it works. So I'm not ready to decide which way is right yet. And the devices are not easy enough to use to just go willy-nilly and apply them just for the heck of it. So I just don't want to do that. I don't want to waste time of others who aren't able to do what I'm able to do, because I know stuff that they don't know. I want to try to bring along people that can do the same stuff I do if I only provide a little help and some resources. And so quantum is just not there yet.
We'll get back
All right,
to you.
good.
Yeah, we can keep going. We don't. The session will not end until the questions do. Can this be used to improve timing of signals? For example, GPS.
The answer is yes. So you look. I already built a clock and oscillator using quantum squeezing. Quantum squeezing is where, look, Heisenberg's uncertainty principle is a great thing, so long as you know how to do the manipulations necessary. Suppose the thing I want to do is measure the position of something. Then I try to do nonlinear operations that take all the noise that's in the position estimator and move it over into the momentum estimator. Because I don't care how much noise there is in the momentum, so long as I get the position correct. Because momentum and position are complementary in quantum systems. The same thing applies in trying to do clocks. So you want the minimum error in the phase angle of an oscillator. You want it to be stable and return to zero at the nearest possible picosecond you can from forever. So if you could do that by taking all the noise from the phase angle and shoving it over into the complementary variable with a nonlinear process, That makes your clock much more stable, much more accurate, and much just everything gets better. And not only that, it stays stable, accurate, and without a lot of jitter and so forth for long time. Eventually, we're going to be able to build a clock in under 10 years that will keep accurate time and of sinusoids to a frequency with the phase always returning to near zero at the right moment for a century without ever having to tune it ever again. We are under 10 years away from that, all due to quantum squeezing.
Very good. I have a applications question for you. As a side benefit to the stated goals, and the thing shifted away from me. Pardon me just a minute. As I think a lot of you know, this platform likes to reset your windows, and I am not immune from that. Okay, so I'm going to ask this question from memory. Now you have a lot of stated goals for classification, signal identification. How does your work in machine learning apply to propagation prediction?
Okay, so you can easily check that I've been involved in radio ionospheric research for quite a while, and I was with the Virginia Tech team that deployed ionosondes all across the country during the last solar eclipse. We will do it again in the upcoming solar eclipse, and now Virginia Tech has 1,000 acres at a farm because Virginia Tech's a land grant college, and there's lots of space out on that farm to put up wire arrays. So we will put up a zigzag linear periodic dipole array as a transmit antenna, and then cross dipoles as receive antennas, and we will learn how to do predictions of what's going on in the ionosphere from the returned ionosondes. And then we will sprinkle the area with these receive antennas, because they're just small non-resonant cross dipoles feeding signals into two ports, so that we can do polarization estimates as well as other things. So the answer, so I'm getting there. Believe me, I am. So all this stuff will go into a database.
So Bob, let me try out something on you. If the machine learning tools detect a strengthening or weakening signal from any given region or country, it would be essentially a propagation tool. Would you agree with that?
It will be a propagation tool, but look, what we really want is something that takes noisy data from several sources and run through this machine learning algorithm, gives a much more accurate prediction of what the state of the ionosphere actually is. And so this is the technical and moral equivalent to super resolution on an image applied to assessment of the state of the ionosphere. You'll take noisy, imperfect data, you run it through a massively trained model, and you will super resolve the state of the ionosphere from this incomplete data.
What's your take on some QST articles about cognitive computer-controlled radios? Do you think that is the future of our hobby?
That is what I'm attempting to do here. Again, I said I was trying to listen to signals, figure out what they were, and automatic pilot build a software-defined radio. So that is a cognitive radio. Now,
okay, you would put that in the category of cognitive radio. it
is indeed, but there's another one. So the student I told you that founded DeepSig is wrote in his PhD thesis an unbelievable result. It is just one of the most beautiful things I've ever seen, and it really turned me on truly for the final time, not halfway in, but all the way in, on to RF-based machine learning. Here's what he did. He took data and he shoved the data into a neural network, and then a bunch of other neural networks followed it and shoved that signal out on the air, and there was a receiver at the other end, and it knew what the data was, but it didn't know what had been done to send it. But it kept giving a feedback on how badly it did to figure out what the signal was. So again, this is supervised learning. And here is the miracle that happened. So after we were doing this naive training of these neural networks for the transmitter, having a channel in between and a receiver, here's what the neural networks did without any input from us as signal processing communications information theory people. It automatically instantiated Oh my God, it automatically instantiated channel compression, followed by channel interference, channel effects mitigation. It just put Shannon right there in it, right in front of us. And after the first thing we realized, this part is taking all this input data and is smashing it down to a compressed version. And then it's taking that compressed version and modulating it up in whatever weird way it wanted to go through this crazy channel and undoes it at the other end. It completely did Shannon's first and second major theorems right in front of us from nothing. It did it from nothing but known data.
So would this help us in receiving data that suffers from severe multipath fading?
The answer is yes, but as always, multipath data is best mitigated by multiple sensors with spatial diversity or frequency diversity. Diversity is your friend.
Yes. Is this, would you call what you're doing the same as artificial intelligence?
No. Artificial general intelligence is the computer and I can interact on a problem, and I can't tell it's not a human. So it'll have to pass the Turing test before I'll call it actual artificial intelligence. So to me, artificial intelligence won't be real until we understand enough about the description of consciousness to say whether or not the computer is both self-aware and self-adapting to its environment, given its awareness. So we're not there yet. I believe we will be. I believe in Ray Kurzweil's prediction as much as anybody in this room probably, but we are not there yet. But it's coming. This is learning how to write stuff down in an encyclopedia, and then later taking the encyclopedia and reading it back. That's not general artificial intelligence.
Okay. There's a question about the data set. For the learning data set, is this based on the samples or in the FFT data?
So the samples, FFT data will be generated in the process, but it will be raw digital samples will be the input.
Okay. What existing audio machine learning matching work are you leveraging? Or have you had to reuse machine learning that was developed for image and photo matching?
That's such a great question. That is really smart. I want to pat this person on the back because that's exactly what I did. I took object identification and tracking done by Tensorflow, took their models, brought them in, and retrained them to look at blocks of signal flowing down a waterfall. So it put them in a little box and identified what they were, and it made a guess, but it put out a stream of answers. I took multiple of them, and I took the 4 best ones and shoved it off to another thing, which zoomed in on the digital samples using polyphase filter bank channelizers, channelize the signal, and figuring out which one of these 4 answers was right. That's a very, very clever question, and they got it exactly right.
Concur. Would a more distributed effort, for example, broader data gathering or processing, help?
Absolutely, and I don't want to just be dependent on K8ND and KA9Q. They have other things they're going to be interested in. The way to make this ultimately successful is get enough people interested in working on it and enough people no data is bad data. That any data I get, I'm going to use, and the more the merrier.
Very good. Okay, that would segue into the next question. There's a set of questions about your email.
GWIER@gmail.com. My GitHub repository is I'm M4HY on GitHub. So there is not yet the machine learning repository. I'm going to move some stuff in there, and it'll be wide open from the get-go. And you'll be able to look at the README and figure out what's there, to figure out places you can contribute. So I want to get just one working block that does this kind of object recognition in there, and then we go from there.
Now,
but there's going to be I'm going to put the collection stuff for the using the nano and the two SDRs in there as quickly as I can get the flow graphs together, which shouldn't take long.
So you will have a README, getting started guide, some sort of general outline guidelines for how to contribute. Okay, thank you. Is there?
And I've used both Slack and Rocket Chat and other things, and I got to tell you, I really like Rocket Chat. So I might start a Rocket Chat thing for us to be able to interact and, laugh and curse with each other and figure out what's wrong and how to do better.
On. Okay. Is there a defined format for samples and tagging that you are using in your body of work?
So okay. So I'm using 16T samples because that's kind of standard. I don't think we ought to need or should use much more than that initially, because I don't want to force people to have high-end gear. If this doesn't work on 8-bit and 16-bit samples, I will be really disappointed. So I don't want you to have to use 32F.
Okay.
And so from there, those will go into TensorFlow records. Now, you don't have to do that. So there will be a shell script, if you will, that will take your input samples and whatever you tell all of us about, and the shell script will run and turn it into TensorFlow records.
Would you be interested in using something like SIGMF from GNU Radio?
I absolutely would.
So that might be a format that would help.
Just in case people don't know, I don't mind telling you. I didn't bring it up because I didn't think it was relevant, but now it's been asked. I will tell you. I held the first. I both stood up and held the first Hackfest. Charles Clancy and I ran the first GNU Radio conference at the University of Maryland. So I wrote the very first FM stereo decoder and a bunch of other stuff that went into GNU Radio. So I've been there for a long time. And people may have detected that around 2006 and 7, major changes happened in GNU Radio. And that was me and Charles Clancy spending government money. Here's
I would call this a theory question, but it does have some very significant applications that I see. The question is, can you improve the signal to noise ratio by using digital signal processing plus machine learning?
Yes. The answer is yes. So look, you take light, you feed it into a video camera, and you apply super resolution to it and make it upsample it so that it has higher resolution. The equivalent of that can be done in signal processing. So my intent is, in a different project but shared here, is to take the Katera SDR, which is 4 4 RTL SDRs in a box, fed into a network which has a noise source so you can cohere them and do passive radar with them. So my intent is to do machine learning based stuff with that. So the answer is yes. So those are fairly low resolution, fairly unstable, but you've got these noise sources which will be shared amongst them that will allow you to tune out the differences between the 4 receivers and then marry them together. I'd love to automate all of that stuff with machine learning enabled algorithms. But look, I'm just one person. I need all sorts of help.
Can CW decoding be a test case for supervised machine learning?
The answer is yes.
I think that it sounds. I don't want to say that that's a straightforward yes, because there's trickiness about CW.
The answer is yes. The answer is yes, and it's the technical and moral equivalent to Jeff Hinton taking scribbled down integers and taking a convolutional neural network and telling you what digit was written down. It's the same thing.
Yes. Here's a question. Is it possible to post the code that that you discussed earlier, where you witnessed that the channel compression, the Shannon effects happened? Is it possible to share that original source code that you and your student did on hardware that we have, such as the NVIDIA Nano, for example?
The answer is I do not believe so, because the student had the software, maintained control of it. What he could not control was, in order to get a degree from a university like Virginia Tech, you are required to publish your thesis and have a public defense. So how he did the work was published in his thesis and in several papers. The code he used to do the work, I'm sure he copyrighted and is now involved in DeepSig patents. So my guess is, my belief is, without being completely certain, and my guess is the answer is no, but we should investigate. And I'm not averse to asking.
Okay, yeah, we'll double check on that. So there is a question in the Q&A tab. It says, it's from Mike Kennedy, and he says, do you have more info on this? And I don't know the context for that question. So Mike, if you would like to let me know in just update in Q&A so that I don't miss the question that you were referring to. Here's a question from Don. He says, so matching static waterfalls is great, but isn't the rate of—
These are not static. These are not static. These are steadily falling.
Right. Yes. That was correct. I'll go ahead and read the rest of it, and we'll just, so that we could draw some good stuff out of here. It's a longer question. So matching static waterfalls is great, and yes, that's not exactly that's not what we're doing. But isn't the rate of change between the signal states interesting as well? Meaning that you're matching images over time. Maybe you would be able to reuse video matching machine learning algorithms, which relates to an earlier question.
So it does relate, because I did reuse existing video algorithms done by Google on object recognition and tracking for objects in a video. So I used that, but I adapted it through transfer learning and other work into identifying blocks of signal moving down a waterfall. So the answer is yes. And so let me go over just the other little piece again. So I knew just looking at this in the frequency domain was not enough. So the waterfall is flowing, and everything that's in the waterfall, from the time it hits the top until it hits the bottom, is also being shoved over into a delay line. So the high-speed digital data that's feeding the waterfall from the top is also over here feeding a digital delay line. And the digital delay line is random access memory. And at the bottom, or around the delay line, looking at this random access memory, is signal processing units that can run DSP algorithms to detect the signal and do fancier things. So I want to work on the original IQ samples where I've been told where to look and an initial guess by looking at it in the frequency domain. So I really want to process it in the time domain, but I got to have something tell me where to look and a nice rough guess. So the looking at the waterfall is where to look, what time to look, and a rough guess. And over here is the fine guess, fine tuning, do it fully at a lower rate because I've compressed the bandwidth.
Could you use this approach to build a machine SSB contest operator?
I believe that the answer to that is getting really close to yes. So I encourage everybody on here to go look at the computer scientists using GPT-3, having a conversation with a bot on the other end. And right now, the machines they had available to them could not do it real time. So they took out all the delay. They took all the latency of going through the GPT-3 process, but when they glued it all back together with all that delay removed, it was like two humans sitting and talking to each other. So I really believe we're getting close. But not yet. The latency is too long.
That is a big challenge with this sort of work. So anything that's interactive that involves language processing of any type, the delay and the latency is the real killer. The thing with an SSB contest or any type of contest is that the alphabet of possibilities is very small. So you're dealing with a limited exchange, and that really does kind of help get some traction on this particular problem. Larry asks, how has machine learning been applied to amateur radio already? Now, this is a very big question. I'm going to pose it to you in this way. What are the projects out there that you know of that have used machine learning with respect to amateur radio?
Okay, so the person brought up Alex Shevkopoulos' work earlier, and that is a bunch of DSP algorithms that are making decisions about what is available to look at on a channel. So that is a very small machine learning based process, and Joe Taylor has done something similar in some of his WSJT software. So the answer is these are small model approaches to doing what I'm talking about doing with much larger models, now that we have hardware that's capable of executing these much larger models. So the hyperparameters for the size of the machine in both Alex Shevkopoulos' work and in Joe Taylor's work are many orders of magnitude smaller than what I'm talking about here. And the only reason we're able to do it is because the hardware has gotten so complex we can finally do it.
When you said earlier, when you said that two things were of moral equivalence, what did you mean by that?
I mean, a better statement is they are analogous enough to take what was done on analog A and apply it to analog B. So you're generalizing what was done for A to apply it to B. They're analogous.
Thank you. Hasn't NSA had signal identification software and hardware available for years?
Yes, and I'm largely responsible for most of it.
Would it be fair to say that that stuff is not really available as open source?
So the answer is it is not available as open source. So what we have to do is redo it using our own methods and approaches. But I'm going to tell you, I was not a fan of doing any of this stuff with neural networks when I left NSA 15 years ago. So I'm sorry, in 2010. So that's 11 years ago. When I left the NSA 11 years ago, I was not a fan of applying machine learning. So all the stuff I've learned to do with machine learning was learned after I left and went to a university. And a university is not a place where students and faculty get by with keeping things secret, because somebody pays them to publish, and then you got to publish and put it out there. So they've done stuff, and I'm sure they've gone very far inside, but I haven't been involved with it, and I don't know what they're doing. And I wasn't doing machine learning when I left there because I thought neural networks were ad hocery.
Oh boy! So would you say that your philosophy and approach and assessment of this particular field has dramatically changed?
Yes. I wish you could see the paper that Charles Clancy, Tim O'Shea, and I wrote in 2008 on cognitive radio. It was Bayesian Bayesian networks, and oh my goodness, it was the amount of computation would have exceeded what the world would eventually be able to do in about a decade, for over a decade, and that was completely washed away when Hinton and others began showing us how you could take these simplified neural networks, train them how to concentrate on one particular part of the problem where they didn't have to deal with the whole universe. They only wanted to look at a certain set of problems and get certain kinds of results, and there was hardware available to do it. That was transformative, and that happened after I did the Bayesian network approach to cognitive radio.
Are you participating in HamSci?
Yes, I'm participating in HamSci.
Okay, and that is the final in the Q&A tab. I'm going back to chat. And I am.
Let's stop in 4 minutes.
Okay, we stop whenever you want or when we run out of questions. What I was going to do is go back to.
No. Let's go 5 minutes and
Okay.
stop. I'm going to lose.
I hear you. What I'm doing is I'm going from the bottom up of chat and I'm looking for things with question marks. And if I think it's the same question that we've already asked, then I won't ask it. Are you familiar with RTX voice? Can we use it for ham radio soon?
I don't know what it is, so I don't know the answer.
Okay. Okay, I think that's been addressed. Let's see. What sensor availability for hams can provide the data you need for spatial diversity?
Okay, what was the question?
What sensor availability for hams can provide the data you need for spatial diversity?
Okay, so the Katera SDR is a 4-input receive-only system. That is nearly ideal. And you can plug it into a Raspberry Pi and run an algorithm that's already published in open source that'll do passive radar. If it can do that, it can do a lot. So I don't intend to plug that thing into a Raspberry Pi 4. I intend to plug it into a Nano. And the Nano has this GPU on it, so I can do 100 to 1,000 times more processing by taking advantage of the GPU. So, but the Katera is a USB plug-in device, and it runs these 4 RTL SDRs. So that's one. Very, very high end would be the Flex 6000 family. Has 2 completely high dynamic range, super stable, super performance, GPS disciplined oscillators costing $6,000 to $7,000 will provide extremely high quality dual channel data.
Are you concerned about patents, and are you going to patent this?
I am not going to patent this. I started Hawkeye 360 Incorporated. That's he360.com, and Federated Wireless. .com, Federated Wireless Incorporated. I started those 2 companies and I patented the ideas to get them off the ground. And I'm done with that. I have, as I said in the talk, and I'll repeat it here with emphasis, this is open source, open specification. None of it will be hidden. It'll be given away to everybody.
Okay, that leads into another comment that's above because there are a lot of FPGA and ASIC GPU libraries, and some of the work that you're talking about doing may be possible with proprietary, or closed source libraries. But one of the main points of your work is to do this in the open, so that people can learn, and so that we all have an open source base to start with. Is that fair to say?
That's fair to say, but nothing stops any individual who downloads the software from plugging their proprietary software and hardware into it if we do the software design right. But they won't be able to distribute it except under the licenses. And you realize if they take GPLv3 software and marry it to that stuff, it inherits.
Are you speculating about the Raspberry Pi GPU, or do you have an inside track?
Oh, no. There was an announcement on multiple websites. I can't point to one right now, but I believe if you go search, you will see there have been public remarks made by people with Raspberry.
Okay. And
I believe I read an article last week with somebody who had their hands on it.
Very good. Okay, here's a person who's just checking with you about their purpose. They're assuming that the big hardware needed to develop the algorithms, that's used to develop the algorithms, and then the model, the implementation will eventually run on very cheap and regular ham gear hardware. Okay, so they just wanted to check to make sure that was the purpose.
I don't want anyone else to have to buy this.
Okay, very good.
I want everyone to be able to spend $59 or $100 on the entire computing complex needed to run it.
Okay, and I think I've caught up with an hour ago. I'm scrolling. If I have missed your question, then take the last minute or two to type it at the very bottom. I'm now going back to the very bottom. There's a question, Bob, what haven't you done? And then asking for links for the Katera. And I think we've got somebody taking care of that.
Well, you can go, tell you what, you can go on academia and look at my webpage, and you will see 50 years of history of things that I've been allowed to publish because they were done in the
okay.
open.
Bob has, I know what
like,
you haven't done. You haven't beat me at poker yet.
That's true. No, I haven't beat my wife at poker either. She whips my tail every time. That and she can take a 45 and shoot the center of her target at 50 paces with nothing except her eyeball. don't want to cross her.
All right, well, we got the edge on Bob and a few items. All right, so any last questions? Let me check in the Q&A tab. It lit up again. Okay, see a thank you. And a question about participating in the work. Similar to the SETI shared, and yes, you can get in touch with Bob directly. It is the email in the chat, and also is N4HY on GitHub. Yeah.
And I'm in QRZ.
Do you recommend any particular book to start with? A good meaty book, a good book. Like if you had to pick one off your shelf to take with you, which one would it be?
Right now, I would this one. Look at that thing, turn things around. Hands-on machine learning with scikit-learn, Keras, and Tensorflow by O'Reilly. Hands-on machine learning with scikit-learn, Keras, and Tensorflow. This is meaty and it's full of stuff.
Okay, so that's a good book recommendation. And we're gonna. This is a Venn diagram of a question. So we talked about FPGAs before. So when we speak of narrowing down the data, narrowing things down and focusing on the data, could it be rewritten for an FPGA? So if somebody that really was interested in targeting it for an FPGA, could that be done?
Yeah. Okay, so before when I said I wanted to stream a wide swath of data, and I wanted to apply spectral techniques to find where the signal was, what frequency it was, and so forth, and do a rough determination of what it might be. Over here, that wide stream of data is flowing into a digital delay line. Well, if that's 30 megahertz of signal or 100, I can do on a CPU aided by a GPU, and probably with ORI and others, we will get access to ultra scale and other things and do it with that, because ultimately for a big machine you're going to need an FPGA. So but down around 10 megahertz, you can do that on a CPU.
Yes, concur. All right, I look forward to working with you on this, Bob, on UltraScale, and to take advantage of some of the wonderful hardware from ARDC. You have a hello from your old Microsat buddy, from David Cowden. He says hi in chat, and lots of compliments. And yes, the slides for these talks will be uploaded. I believe it's going to be, I'll make sure that it gets uploaded on this platform. The plans for this particular event are for it to remain up for 30 days. And then after that, all of these presentations and all of the slide decks will be available for good. YouTube, Vimeo, it's going to be one of those two things. So check in with the QSO Today website, or those of us that are kind of active and have helped with the talks will also try to spread the word. So the answer about the slides, yes. If you would like a copy of the slides now, the best way to get it is to write Bob directly and ask him for a copy, and you'll get it really fast.
What I will probably do is put them up on my Google Drive and make a publicly available link available. I will let you have it, and you can put it on ORI or wherever, so it gets widely distributed.
We'll scatter it around. It'll be out there. So thank you, everybody.
It'll be scattered. Yeah. I'm not interested in keeping it a secret because I won't.
Okay. And
Okay, I think we should quit.
Yeah, before you lose your voice entirely, we will go ahead and
That was
yeah,
perfect.
we'll quit. Thank you, everybody. Again, if you have any further questions, please write Bob or me, and we will get the answer to you.